The ocean was calm that morning, eerily calm. No storm clouds on the horizon, no roaring waves, no enemy submarines lurking below. Yet, as dawn broke over the Atlantic, a thunderous crack echoed across the still water. A Liberty ship fully loaded with cargo began to tear apart, right down the middle. Steel screamed as the hull split in two, the bow rising grotesquely before sinking beneath its own weight. Within minutes, a vessel that had taken weeks to build and was supposed to carry supplies to the front was gone, swallowed by the sea it was meant to conquer. This wasn't an isolated event. It was one of many. The year was 1943, and America was losing ships faster than it could build them, not to enemy fire, but to physics itself. The Liberty ship program had been the pride of American industry. These vessels were the lifeblood of Allied logistics during World War II, ferrying food, ammunition, tanks, and troops across treacherous oceans. They were mass-produced marvels of efficiency, designed to be built quickly and cheaply so that no amount of German U-boats or Axis blockades could choke off supply lines. But somewhere along the line, something had gone terribly wrong. In calm harbors and mild weather, ships were cracking open without warning. Some snapped in two at dockside, others broke apart at sea under light waves. Over 1,500 vessels reported serious structural cracks. 19 of them split completely in half. 3 simply vanished, leaving only debris and rumors behind. The government tried to keep the failures quiet. Wartime censorship was tight, and officials feared that public knowledge of ships breaking in half would devastate morale and confidence in the war effort. But in shipyards up and down the coast, whispers spread among workers and engineers alike. The Liberty ships had a fatal flaw. The very technology that had made them possible was now threatening to destroy them. That technology was welding. Before the war, ships were built the traditional way, using rivets to fasten metal plates together. It was slow, labor-intensive, and required skilled craftsmen. But as the war escalated, time became the enemy. Riveting took months. Welding could do it in weeks. Welding was faster, cheaper, and didn't need as much expertise. For Henry J. Kaiser, the industrialist leading America's shipbuilding miracle, welding was the key to outproducing the enemy. So Liberty ships were made entirely of welded steel, the first large vessels in history built that way. What no one anticipated was that in switching from rivets to welds, they had introduced a new kind of danger, one that couldn't be seen until it was too late. Inside the steel plates of every Liberty ship, invisible stresses were building. The problem was something called brittle fracture. Unlike ductile metals that bend before breaking, brittle materials fail suddenly, like glass shattering. When cracks formed in welded joints, sometimes from tiny imperfections, sometimes from cold temperatures, they didn't stop. They ran, fast and unstoppable, racing through the metal at the speed of sound. A small flaw the size of a coin could, under the right conditions, become a gaping split that tore an entire ship in half. Engineers were mystified. They tested the steel and found it met specifications. They blamed impurities or the bitter cold of the North Atlantic. Some even suspected sabotage, but no theory fully explained the sheer scale of failure. Meanwhile, the pressure to produce more ships never stopped. America needed hulls, not excuses. At Kaiser's massive Richmond shipyards in California, production continued around the clock. Thousands of workers, many of them women who had never held a torch before the war, welded day and night to meet impossible quotas. Among them was a woman named Bessie Hamill. She was no scientist, no engineer, and certainly no one the newspapers would write about. She was a night shift welder, one of tens of thousands who made up the invisible army behind America's maritime power. But Bessie had something most didn't: an eye for patterns and the stubbornness to question what everyone else accepted. It started with an observation. Night after night, Bessie noticed that certain sections of the ships she worked on developed hairline cracks shortly after being welded, while others held perfectly fine. At first, she thought it was coincidence, or maybe bad steel. But the more she watched, the more she noticed a pattern. The cracks seemed to appear when welders worked in a particular order, especially when they moved sequentially along the hull without alternating sides. She began taking notes, sketches, times, temperatures, even which welders were assigned to which section. Over weeks, her logbook filled with data no one had asked her to collect. She was sure she was onto something, but when she brought it up to a supervisor, she was met with polite dismissal. "You're overthinking it, Hamill," one foreman told her. "Just stick to your section. The engineers will handle the cracks." But the engineers weren't handling it. Ships kept failing, and no one could explain why. So Bessie kept watching. She started experimenting quietly, changing the order of her welds whenever she could get away with it. When she reversed her sequence, starting from the edges and working inward instead of along one continuous line, the cracks stopped forming. She tested it again and again, with the same result. It was such a simple change that it seemed almost ridiculous. But in her mind, something clicked. The sequence of welding wasn't just a matter of efficiency, it was changing how the steel cooled. And that cooling process, she suspected, was locking invisible stresses into the hull. What Bessie had stumbled upon was the concept of residual stress, though she didn't yet know the term. Every time a weld cooled, the metal contracted slightly, pulling against the plates around it. When welds were laid in a certain order, those contractions compounded, creating tension that weakened the structure long before it ever touched the water. The engineers had focused on materials and temperature. Bessie was looking at the process. Her ridiculous observation, as one skeptical supervisor called it, would soon prove to be one of the most important insights in wartime engineering. Word of her theory spread quietly among the night shift welders. Some began copying her method, not because they believed her, but because it made their welds look cleaner. Within weeks, supervisors noticed something odd. Sections welded by Bessie's team were holding up far better during inspections. Cracks were down, rework was reduced, and production moved faster. Eventually, the pattern became impossible to ignore. Kaiser's engineers decided to test her method formally. They set up controlled welds, some done the traditional way, others following Bessie's reversed sequence. When the results came in, the difference was undeniable. Welds done in Hamel's order distributed stress evenly across the plates, dramatically reducing fracture. The ridiculous trick wasn't ridiculous at all. It was revolutionary. For the first time, the mystery behind the Liberty ship failures began to make sense. The problem wasn't just the steel or the cold. It was how the ships were being welded. Bessie Hamel, an untrained night shift worker, had solved what some of the nation's top metallurgists could not. Her discovery would soon ripple through every shipyard in the country. Engineers began redesigning welding procedures based on her findings, developing new stress relief techniques and inspection protocols. What had been a desperate race against time became an orchestrated industrial miracle. Her insight did more than save ships, it transformed how they were built. The Liberty ship crisis had exposed the dark side of rapid innovation, but Hamel's observation turned that failure into progress. By changing welding sequences, builders could now push speed without sacrificing safety. That small shift in understanding would pave the way for the next generation of ships, the Victory ships, faster, stronger, and far more reliable than their predecessors. The transition from Liberty ships to Victory ships marked a turning point in wartime manufacturing, but it wasn't just about building faster. It was about rebuilding trust. The failures had shaken confidence in America's arsenal of democracy, and every ship that cracked was a blow to national pride. But the new methods inspired by Bessie Hamel's discovery changed everything. At the Richmond shipyards, Kaiser's teams restructured their workflow. Welding crews were retrained in the new sequence, and quality inspectors began focusing on stress lines instead of just surface appearance. Almost overnight, fracture reports plummeted. The shipyards that had once been plagued by mysterious failures were now turning out vessels that could withstand the harshest Atlantic storms. These innovations didn't stop at the welding lines. With the stress problem solved, engineers could finally turn their attention to efficiency. The Richmond yards became the most advanced shipbuilding operation in the world, a massive symphony of steel, sweat, and precision. The production process resembled an assembly line more than a traditional shipyard. Hull sections were built in separate bays, pre-fitted with wiring, piping, and bulkheads, then rolled into place and welded together like puzzle pieces. What had once taken 40 days now took less than a week. The workers themselves called it Kaiser's magic, but those who understood the process knew it was the culmination of thousands of small improvements, each one a spark of innovation from ordinary people like Bessie. One of the crowning achievements of this transformation came in late 1942, when Kaiser's team decided to push the limits of what was possible. They announced they would attempt to build an entire Liberty ship in record time, not in weeks, but in days. Skeptics laughed. The fastest ship so far had taken 10 days, and even that was considered a miracle. But Kaiser was a man who thrived on the impossible. The project was dubbed the 5-day ship. It would be a demonstration of what American industry, armed with new knowledge and unshakable will, could do. For 5 days straight, the Richmond yard never slept. Floodlights turned night into day. Welding sparks lit up the bay like fireworks. Men and women worked in rotating shifts, fueled by coffee, adrenaline, and patriotism. Every hour was choreographed to perfection. Prefabricated sections were lowered into place by cranes, crews swarmed over decks, welders sealed seams, electricians wired cabins, all in a frenzy of synchronized motion. On the fifth day, at 4:15 a.m., the ship slid into the water. Her name was the SS Robert E. Peary, and she had been built in 4 days, 15 hours, and 29 minutes. A world record. The crowd that gathered to watch the launch erupted in cheers. Newspapers called it the ship that broke the clock. But what few people knew was that this record-breaking feat was made possible because one welder, months earlier, had noticed cracks forming where they shouldn't have been. The Robert E. Peary was more than a ship. It was proof that American ingenuity could adapt, learn, and overcome. Each welded seam carried within it the invisible signature of Bessie Hamel's discovery. Her revised welding sequence had been adopted not only at Richmond but across the entire Maritime Commission program. The improved structural integrity allowed shipbuilders to push welding speed to new heights without fear of catastrophic failure. As a result, production skyrocketed. Between 1941 and 1945, more than 2,700 Liberty and Victory ships were built, enough to create a virtual conveyor belt of supplies stretching across the ocean. But while the shipyards roared with success, Bessie herself remained largely anonymous. Her supervisors knew what she'd done, but wartime bureaucracy had no room for individual recognition among industrial workers. Official credit went to engineers who formalized her findings into written procedures. In internal memos, her contribution was sometimes referred to only as operator feedback on weld sequencing. To her fellow workers, she was still just Bessie, the night shift welder who worked quietly and never boasted. Yet those who knew her understood that her keen observation had likely saved hundreds of lives. Behind every ship that sailed safely across the Atlantic was the unspoken legacy of that observation. The phenomenon she had identified, residual stress, would become a cornerstone of post-war engineering. Scientists and metallurgists began studying it in depth, developing mathematical models to predict how welded materials behave under load. Entire new fields of research opened up, leading to the birth of fracture mechanics and finite element analysis decades later. In a way, Bessie's discovery foreshadowed the digital simulations and stress tests used in modern construction. She had done it with nothing but her eyes, her hands, and a notebook. Yet for all the progress, the lessons of the Liberty ship crisis came at a heavy cost. The early failures had claimed lives, not just from sinking ships, but from explosions and accidents in the shipyards themselves. Welders worked under dangerous conditions, often breathing toxic fumes with little protection. The pace was relentless. Many workers were women or minorities who had never been given industrial jobs before the war. They worked 12-hour shifts, 6 days a week, in cold and heat, through fatigue and injury. The war demanded sacrifice, and the shipyards became a battlefield of their own, a place where human endurance was tested as much as steel. Still, there was pride. Every time a new ship slid down the ways, the workers cheered as if they'd launched a battleship. For many, it was the first time their labor had a visible, tangible purpose. They knew their ships were feeding armies, rescuing prisoners, and keeping the Allies alive. That sense of purpose carried them through exhaustion and danger. And even if most never knew the details of Bessie Hamel's insight, they felt the results in their daily work. Welders found fewer cracks. Inspectors passed more sections. Morale improved. The shipyards became symbols of unity and strength, factories that could build a ship faster than the enemy could sink one. As the war drew on, the improved ships began to make their mark. The new Victory-class vessels, designed with lessons from the Liberty failures, were faster, sleeker, and stronger. Their hulls resisted cracking even in the icy waters of the Arctic convoys. Supply lines stabilized. The tide of war began to shift. American and Allied forces could now rely on a steady flow of equipment, fuel, and food. The same industrial spirit that had once produced flawed ships now produced the backbone of victory. And somewhere in that transformation, buried under layers of bureaucracy and history, was the legacy of one woman's ridiculous observation. After the war, when the shipyards fell silent and the torches went cold, many of the workers returned to ordinary life. Bessie Hamel was among them. Records of her personal life are scarce, but it's believed she continued working in industrial welding for several years before retiring quietly. Her notes and logbooks, which she had kept during the crisis, were stored away, forgotten by most. It wasn't until decades later, when engineers and historians began re-examining the Liberty ship failures, that her name surfaced again. In archived interviews with shipyard workers, several mentioned a woman welder who figured out the cracking problem. Investigators traced these accounts back to Bessie. Though there was no formal citation, her contribution began to be recognized in engineering circles as an example of grassroots problem-solving, proof that observation and persistence can change the course of history. In a sense, her story encapsulates a universal truth about innovation. The greatest breakthroughs often don't come from those in power, but from those who see the world differently, from the shop floor, not the boardroom. Bessie didn't have a degree, but she had what many engineers lacked: proximity. She was close enough to the work to see what others missed, to feel how the metal behaved, to notice patterns invisible to those working from blueprints and theories. And when she spoke up, she was brave enough to challenge authority in an environment where doing so could easily get her dismissed or ignored. That courage is what made her discovery possible. The tragedy, of course, is that she never received the recognition she deserved during her lifetime. Her contribution faded into the background of wartime anonymity, her name absent from official reports and textbooks. Yet, in every welded structure built since, the bridges that span rivers, the skyscrapers that pierce the sky, the pipelines that carry energy across continents, the principles she uncovered live on. Every time a modern engineer designs a weld sequence to minimize residual stress, they are unknowingly echoing the insight of a night shift welder from 1943. The post-war years were an era of unprecedented industrial growth. America's wartime factories, once devoted to tanks and ships, were converted to produce cars, appliances, and the infrastructure of the modern world. Welding, once considered a rough-and-ready shortcut for emergencies, became a refined science. The lessons learned in the shipyards, born of crisis, error, and discovery, now shaped everything from bridges to skyscrapers. Engineers began to codify welding practices into national standards, drafting procedures that dictated everything from temperature control to sequence order. Embedded within these regulations, though uncredited, was the ghost of Bessie Hamel's idea: always consider the order of operations, because how you build is as important as what you build. At universities and research institutes, metallurgists analyzed the failures of the Liberty ships with the precision of detectives. They cut sections of old hulls, examined fracture patterns, and simulated the stress conditions under which cracks had formed. What they found astonished them. The ships hadn't failed because of bad steel, as many had claimed, but because of the way the steel had been welded and cooled. Residual stresses, the locked-in tensions created by the welding process, had combined with low temperatures to create brittle conditions. When those stresses reached a critical point, the hull simply tore apart. The engineers who studied these failures often marveled at how close the shipbuilders had come to disaster without understanding why. Yet somewhere in the chaos of the Richmond night shifts, one person had instinctively found the answer. By the 1950s, fracture mechanics had emerged as a discipline, led by figures like Alan Griffith and George Irwin, whose work quantified what Bessie had intuitively grasped. They developed mathematical models to predict when a crack would propagate, how fast it would travel, and what could stop it. Engineers began designing structures with crack arresters, deliberately placed joints or materials meant to prevent sudden failure. In every conference paper and technical journal, one could trace the echoes of the Liberty ship crisis. Though Bessie's name was never cited, her fingerprints were there. In every diagram of stress distribution, in every textbook that warned against sequential welding, in every safety protocol meant to prevent another wartime catastrophe. Meanwhile, the Victory ships themselves became a symbol of resilience. Longer and stronger than their predecessors, they served long after the war ended. Many were repurposed as merchant vessels, troop carriers, or training ships. They sailed under various flags, crossing oceans that had once swallowed their ancestors. The very first Victory ships bore plaques celebrating America's industrial might, but not the invisible insight that had made them possible. When historians toured the shipyards decades later, they found rusted cranes and abandoned docks, but also a lingering spirit: the idea that ordinary workers, through observation and ingenuity, could solve problems that experts could not. Bessie Hamel's story might have ended there, buried under the anonymity of history, if not for the curiosity of a new generation of engineers. In the 1970s, as universities began compiling oral histories from World War II industrial workers, Researchers from the Smithsonian interviewed dozens of welders who had worked at the Kaiser yards. Over and over, one name came up. There was a lady named Hamill, one recalled. She figured out why the ships cracked. Another remembered her carrying a small notebook full of diagrams and weld sequences. She always said, "Don't just look at the metal, listen to it." The researchers, intrigued, dug deeper. Personnel records confirmed a Bessie Hamill employed at Richmond between 1942 and 1945. She wasn't an engineer, just listed as welder, night shift, Bay 4. Yet her name appeared again in an internal memo from 1944 describing operator feedback resulting in improved weld performance. It was a faint trace of credit, but a trace nonetheless. Even with such limited evidence, her story began to spread. Articles in engineering magazines mentioned an unnamed welder whose insights helped solve the Liberty ship crisis. Eventually, historians pieced together enough testimony to restore her name to the narrative. Though she had died years earlier, her contribution was finally acknowledged, quietly but meaningfully, in academic papers and maritime museums. The Richmond Shipyard's National Historical Park now includes a brief mention of her in its exhibits, honoring the anonymous innovators who made victory possible. It's not a monument or a statue, but it's something, a recognition that history is often written by those who never meant to make it. The deeper truth of her story lies in what it reveals about innovation itself. Great discoveries often happen not in laboratories, but in the margins, in the spaces where theory meets experience. The shipyard was a crucible of human intuition and trial and error. Engineers designed from blueprints, but welders like Bessie lived inside the problem. They could see the metal contract, feel it tense, hear it hiss as it cooled. To them, steel wasn't abstract. It was alive, temperamental, and full of secrets. When Bessie noticed the cracks forming in a pattern, she wasn't just being observant, she was listening to the material's story. Her notebook was less a scientific record than a conversation between human and machine, between instinct and evidence. And yet, it's easy to imagine how close that insight came to being lost. In a different world, Bessie might have shrugged off the cracks as someone else's problem. She might have accepted her supervisor's dismissal and stopped taking notes. If she had, hundreds more ships might have failed, thousands more lives might have been lost, and the course of wartime production could have shifted. That's the fragile nature of progress. It often hinges on one person's refusal to look away. The physics behind her discovery, brittle fracture and residual stress, remain among the most important concepts in modern engineering. To explain them simply, when metal is welded, it heats and expands. As it cools, it contracts, but not uniformly. Different parts cool, at different rates, creating internal tension. Imagine trying to freeze a balloon from one side. The surface tightens unevenly, and cracks can form where the stress is highest. In a welded ship hull, those stresses can be immense. When combined with low temperatures, like those of the North Atlantic, they make the steel more brittle. The result is a ticking time bomb. A single flaw, even microscopic, can trigger a chain reaction. What Bessie realized without equations or formulas was that changing the order of welds could prevent those tensions from aligning destructively. Her reverse sequence method essentially gave the metal time to breathe, to settle before locking in stress. It was a masterstroke of intuition, the kind of insight that feels obvious only after someone has pointed it out. In the decades that followed, her method became a standard part of welding instruction. Apprentices were taught to alternate welds, to balance heat distribution, to avoid creating stress paths. These rules are now codified in the American Welding Society's guidelines and the Navy's shipbuilding protocols. Few who study them realize their origins trace back to a wartime welder's experiment. But that's the nature of knowledge. It spreads quietly, shedding names as it travels, becoming collective wisdom. As time went on, the story of the Liberty ships became both a cautionary tale and a triumph. Universities taught it as a case study in failure analysis, how rushing innovation without understanding can lead to disaster, and how curiosity can turn disaster into progress. For young engineers, it became a lesson in humility. The Liberty ship showed that even when a design meets every specification, nature may still have the final say. And the tale of the welder who saw what the engineers missed became a parable about the power of paying attention. The legacy of Bessie Hamill isn't just technical, it's deeply human. It speaks to the courage of those who stand at the edge of knowledge and say, "Something's not right." It reminds us that systems, however grand, are built from the perceptions of individuals. Every blueprint, every formula, every innovation begins with someone noticing a small, inconvenient detail. In the rush of war, Bessie noticed, and because she noticed, the world learned. The Liberty ships that had once cracked apart in the quiet waters of American harbors were replaced by the sturdy silhouettes of the Victory ships, each one a floating testament to the power of adaptation. They were longer, with more powerful engines and improved steel alloys, but the true advancement lay beneath the surface, in the invisible science of stress control. The welders who built them were no longer improvising in the dark. They worked with carefully sequenced plans, guided by new techniques that balanced speed with structural integrity. The lessons learned from failure had been woven into every seam. Each new launch was a symbolic redemption, a declaration that the mistakes of the past had been understood and overcome. In the years immediately following the war, America's industrial success was celebrated in documentaries, newsreels, and public exhibits. The Kaiser shipyards, once a place of constant clanging and flame, became an emblem of wartime unity and production power. Yet, as those stories were told, the spotlight remained fixed on the great industrialists and the men in suits who had coordinated the effort. Rarely did the camera linger on the workers who made the revolution possible. The women who had taken up welding torches, who had sweated and strained through long nights, were thanked for their service and then quietly ushered out of the factories as the men returned home. Their contributions, so vital during the war, became a footnote in the peacetime economy. For Bessie Hamill, that erasure must have felt familiar. Her discovery had saved ships and lives, but she never became a public hero. She went back to being invisible, one worker among millions whose names history never wrote down. But even invisibility has a kind of endurance. The effects of Bessie's insight rippled outward through time, influencing fields she would never see. As the Cold War dawned and industries turned toward building jet aircraft, nuclear submarines, and space rockets, the same principles of stress management applied. In aerospace engineering, weld sequencing became critical for controlling the microscopic cracks that could destroy pressurized fuselages. In nuclear construction, the prevention of residual stress became essential for reactor safety. What had begun as a wartime workaround in a shipyard became a universal truth of manufacturing. The sequence of creation determines the strength of the whole. It's remarkable to think that such a revelation came not from theory, but from observation. Bessie didn't have graphs or charts, only what her senses told her. She saw patterns, she trusted them, and she tested her own assumptions. In that way, her process mirrored the essence of scientific discovery. She was performing experiments in real time, guided by intuition and the feedback of her environment. In modern terms, she was practicing empirical design thinking decades before it had a name. Her torch was her laboratory, her ships, her experiments. The war had forced innovation to happen everywhere, from laboratories to assembly lines. But in Bessie's case, innovation happened in the quiet hours of the night, between the sparks of molten steel. It's easy to romanticize those years, to see them as a golden age of ingenuity, but the reality was harsher. The shipyards were dangerous. Every worker knew someone who'd been injured by heat, crushed by equipment, or sickened by fumes. There was little time for rest, and mistakes could be fatal. The pressure to produce was unrelenting, and failures carried not just technical consequences but moral weight. Each ship lost. To fracture meant supplies that wouldn't reach soldiers, allies who might die waiting. That burden hung over everyone, from engineers to welders. When Bessie's method began reducing failures, the sense of relief was palpable. Workers felt as if they'd finally gotten ahead of the war itself. For once, they weren't just reacting, they were solving. And yet, even as the shipyards perfected their craft, the sea remained an unforgiving teacher. In 1944, one of the last major Liberty ship fractures occurred off the coast of Alaska. The SS John P. Gaines, sailing through freezing waters, cracked in two and sank within minutes. The loss reignited old fears, but the investigation confirmed what Bessie had already understood. The welds had been laid in the old sequence. The ship's construction had missed the memo, literally. New methods had not yet been standardized across all yards. It was a tragic reminder that progress moves unevenly, that even the best solutions take time to reach every corner of an industrial empire. After that incident, the revised procedures were made mandatory. No new ship would ever be built without them. It was a victory won in hard lessons, sealed by the sacrifices of those who came before. After the war, the shipyards closed, But the workers who had built the Liberty and Victory fleets carried their experience into new industries. Many of the women who had welded ships took jobs in construction or manufacturing, breaking barriers they hadn't even known existed before the war. The Rosie the Riveter generation became the quiet architects of post-war America. They built factories, bridges, and highways, carrying with them the knowledge that precision and observation could change everything. In that sense, Bessie's legacy lived on in the hands of thousands. Every time a welder paused to inspect a joint or adjusted a sequence to balance stress, they were channeling her spirit. In academic circles, engineers continued to dissect the Liberty ship phenomenon for decades. Conferences dedicated sessions to the topic, analyzing it as a case study in systems failure. Papers were published with titles like Lessons from Liberty, The Evolution of Structural Integrity, and Residual Stress in Welded Hulls, a Historical Perspective. The Liberty ships became a foundational story in engineering ethics, a reminder that technology, no matter how advanced, must respect the laws of nature. Professors told their students that arrogance had sunk those ships as surely as icebergs had sunk the Titanic. And in the midst of all that discussion, the story of the welder who noticed the cracks became a whispered legend, a symbol of humility and perseverance. Her name might not have been on the papers, but her spirit was in the footnotes. By the 1980s, a new generation of historians began revisiting the contributions of women in wartime industry. Books and documentaries highlighted the overlooked innovators, the factory workers, code breakers, and technicians whose insights had changed the course of history. Among them, a small but growing number of researchers began citing Bessie Hamill by name. They reconstructed her story from interviews, shipyard records, and technical reports. Though much of her personal life remained unknown, her professional impact was clear. One historian described her as the woman who taught steel to behave. Another wrote, Bessie Hamill was not an engineer, but she did what engineers dream of. She made the invisible visible. It's hard to imagine how she might have felt had she known how far her discovery would travel. In her time, she was likely just proud to see the ships leaving the dock intact, proud to know that the men at sea could trust the work she'd done. She might not have thought of herself as a pioneer or a scientist, but that's what she was. Her curiosity bridged the gap between theory and reality, between human intuition and mechanical truth. And perhaps in some way that's the most enduring kind of innovation, the kind that doesn't begin with ambition but with care. She cared enough to notice. She cared enough to keep watching when others stopped, and because of that, she changed the world. When historians look back at the 20th century, they often focus on the visible symbols of progress: rockets, skyscrapers, highways, computers. But beneath all those marvels lies a subtler revolution: the mastery of materials. The ability to understand and control how things break, how they bend, how they hold together under stress, is what made modern civilization possible. That revolution began in places like the Richmond shipyards, in the glow of welding torches and the hum of determination. And in that glow, somewhere on a night shift in 1943, stood Bessie Hamill, watching a seam of molten steel cool into place, seeing not just the light but the lesson within it. As America moved further into the post-war decades, the pace of innovation didn't slow. It accelerated. The same factories that had once churned out Liberty and Victory ships now turned to building peacetime marvels: airplanes, power plants, and the steel skeletons of a new generation of cities. The knowledge gained from wartime welding found its way into every corner of modern life. Engineers and tradespeople alike spoke a new language of precision and safety, guided by the hard-won lessons of the 1940s. Behind that evolution was an unspoken truth. The war had forced humanity to grow up fast, to learn that progress without understanding is a recipe for catastrophe. In that respect, the story of Bessie Hamill and the cracking ships became a quiet moral parable that lingered in the background of industrial culture. In classrooms across the country, professors used the Liberty ship failures to teach future engineers about humility. Diagrams of fractured hulls appeared in textbooks, annotated with arrows showing where stress lines converged, where cracks had originated, and how the welds had failed. For students, these weren't just mechanical details, they were cautionary symbols. The ships had met every requirement on paper, yet still they'd failed. Why? Because the engineers hadn't understood how the real world behaves when metal meets cold, when theory meets practice, when ambition outruns patience. The Liberty ships reminded everyone that nature doesn't negotiate, it only responds to truth. That truth had been uncovered not in a university lab, but by a woman working through the night, staring at molten seams and seeing what no one else could. By the 1960s, welding had become one of the most sophisticated trades in the world. Automatic welding machines, new alloys, and advanced inspection methods changed how things were made. But one thing remained constant: the principle that stress must be balanced and sequence must be respected. Bessie's insight was embedded so deeply in the craft that no one even questioned it anymore. It had become instinct. "Don't run all your welds in a line," older welders would say to apprentices. "Balance your heat." They might not have known her name, but they were repeating her wisdom word for word. It's strange how an idea can outlive its creator, stripped of its origin yet immortal in practice. Meanwhile, historians continued to unearth fragments of her life. They found that Bessie Hamill had been part of one of the first integrated crews at Richmond, a team of men and women from diverse backgrounds, all trained under the same urgency. They found payroll slips, time cards, and work schedules bearing her name. One document mentioned her as part of a quality control pilot program, suggesting that her observations might have been formally recognized within the yard's internal structure. If that was true, it meant that, at least among her peers, her contribution wasn't entirely forgotten. But in the larger narrative of American industry, her name remained obscure. It was as if her story had been welded into the framework of history, strong, necessary, but unseen. To understand why her discovery mattered so much, one must imagine the scale of the problem she helped solve. Each Liberty ship was a massive structure, nearly 440 feet long, made up of thousands of steel plates welded edge to edge. When one section cracked, it wasn't just a small defect. It could trigger a chain reaction that raced across the hull in seconds. Entire ships could, and did, tear themselves apart from a single flaw. The shockwaves of those failures weren't just physical, they were psychological. For a time, there was genuine fear that the welding revolution had been a mistake, that the dream of fast, efficient shipbuilding had doomed the fleet. The fact that one welder's observation helped reverse that fear is almost beyond belief. Her solution restored confidence in the process, not just technically, but emotionally. It told an entire nation that the tools of progress could still be trusted if used wisely. The war had demanded speed above all else. The shipyards were laboratories of controlled chaos where innovation was born not from research, but from necessity. Every shortcut came with risk. Every risk carried the potential for disaster. When the Liberty ships began breaking, it exposed the limits of that philosophy. But rather than retreat, America adapted. Bessie's insight was part of that adaptation, a small act of correction that realigned the trajectory of an entire industry. In a sense, she reintroduced balance into the equation, between speed and care, between production and reflection. Her method didn't slow the work, it simply made it smarter. And that's what true progress looks like. Throughout the 1950s and 1960s, the principles she'd uncovered began to shape modern engineering education. Universities developed new courses on materials science, fracture mechanics, and stress analysis. Engineers learned to think not just about materials, but about the invisible forces inside them. They built mathematical models, ran simulations, and created safety factors that accounted for human error. But the seed of that entire discipline was a simple observation: that the order in which you weld metal matters. From that observation grew an entire branch of physics dedicated to understanding how things fail and how to prevent it. One of the most enduring legacies of the Liberty ship crisis is how it reshaped the relationship between engineers and workers. Before the war, there was a rigid divide. Engineers designed, workers built. Communication flowed one way, from the drawing board to the assembly line. But the crisis blurred that boundary. When the ships began breaking, everyone had to listen. To welders, inspectors, riveters, anyone who could provide insight. Bessie's story embodied that shift. She wasn't supposed to solve the problem, but she did. And in doing so, she proved that expertise doesn't always come from authority. Sometimes it rises from experience. After the war, many industries began formalizing worker feedback systems, allowing those on the front lines of production to report flaws, suggest improvements, and share observations. That philosophy, continuous improvement through communication, became a cornerstone of modern manufacturing. In a way, every safety culture, every quality assurance protocol, owes a small debt to Bessie Hamill. Her discovery also influenced how industries approached failure itself. Before the Liberty ships, failure was seen as shameful, something to be hidden or denied. But after, engineers began to treat failure as data, a signal pointing toward a deeper truth. The ships that cracked became teachers. They showed that progress isn't linear, that mistakes are part of the journey. Bessie's willingness to look closely at those cracks, to treat them not as disasters but as clues, exemplified that new mindset. In her quiet persistence, she turned catastrophe into curiosity. That attitude would come to define post-war science and engineering culture, paving the way for iterative design, systems thinking, and the safety-first approach that underpins every modern project. As the decades rolled on, the shipyards fell silent, their cranes rusting against the sky. But the echoes of their labor lived on in the ships that still plied the world's oceans. Some of the last Victory ships remained in service well into the late 20th century, converted into training vessels or museum exhibits. Visitors walking their decks today can still see the clean, confident welds that replaced the fractured seams of the early days. Those lines of steel tell a story of failure, learning, and redemption. They are the fingerprints of a generation that built faster than anyone thought possible, and of one woman who helped them build better than they ever had before. For all her anonymity, Bessie Hamill's influence endures every time a welder strikes an arc, every time an engineer checks a stress diagram, every time a structure holds when it might have failed. Her story is proof that the smallest observation can ripple across history, that even the quietest voice can reshape the world. In the grand tapestry of World War II, where so many heroes are remembered for bravery on the battlefield, hers is a different kind of courage, the courage to notice, to question, and to persist when no one is watching. By the time the 20th century reached its midpoint, the world had entered a new era of construction. Cities were reaching higher, ships were sailing farther, and machines were being built to withstand forces unimaginable a generation before. Every skyscraper, every bridge, every submarine carried within it the inheritance of lessons learned in wartime, lessons forged in sweat, steel, and error. The ghosts of the Liberty ships haunted every engineer who ever signed off on a design. They were a constant reminder. Perfection on paper means nothing if reality disagrees. And so, out of failure came a culture of testing, verification, and continuous learning. That was Bessie Hamill's world. Writ large, the idea that to make something last, you have to understand how and why it breaks. In this new world, the tools of discovery evolved. Where Bessie had once relied on her eyes and hands, engineers now used stress gauges, strain rosettes, and X-ray diffraction to measure internal forces. Computers began to model how heat moved through metal, predicting the very same distortions she had observed intuitively in 1943. It's almost poetic. What she felt with her fingertips, modern scientists could now simulate with equations. Yet even with all that technology, the underlying principle remained the same. Every weld, every joint, every connection still had to be made in balance. You could measure stress to the thousandth of a pound, but if you ignored sequence, the structure would still fail. Machines could calculate, but they couldn't see the way Bessie had seen. Seeing not just with the eyes, but with the kind of understanding that comes from living inside the problem. As her story slowly resurfaced through oral histories and academic curiosity, it began to take on a life of its own. In documentaries and museum exhibits, she became a symbol not just of technical brilliance, but of a deeper kind of wisdom, the kind that comes from being willing to question routine. Interviews with surviving shipyard workers painted a portrait of a woman who was patient, meticulous, and quietly confident. She didn't shout, one recalled. She just kept showing us what she meant over and over until we could see it for ourselves. That description captures something profound about innovation. It often spreads not through argument, but through demonstration. Bessie didn't need authority to be right. She needed evidence. And in the face of evidence, even skeptics had to listen. Her discovery also underscores a truth about gender and recognition during the war. Thousands of women had joined the workforce, taking on jobs once reserved for men: machinists, welders, riveters, electricians. They had proven their competence beyond doubt. Yet when the war ended, many were pushed out of those roles, their achievements minimized or forgotten. Bessie's story fits that pattern all too well, an extraordinary contribution written out of the official record simply because of who made it. For decades, the face of innovation remained male, even though the hands that built so much of it were not. Only recently have historians begun to correct that imbalance, shining light on the quiet revolutions led by women in factories, laboratories, and offices across the nation. Among those rediscovered names, Bessie Hamels stands as a symbol of resilience, not just in steel, but in spirit. If you walk through the remains of the Richmond shipyards today, you can still feel the echo of that era. The docks stretch toward the bay like scars of history. The air carries the faint scent of salt and rust. Where cranes once moved day and night, seagulls now perch in silence. Yet the ghosts are there. The welders, the riveters, the foremen shouting over the din of metal, the shift whistles calling workers to their posts. Somewhere among them, imagine Bessie, helmet down, torch in hand, sparks dancing in front of her as she watches the orange line of molten metal cool into steel. That was her world. Noise, heat, precision, and responsibility. She probably never thought that moment would echo 80 years into the future. She was simply doing her job, doing it well, doing it with care. But history is often made by those who think they're just doing their job. The Liberty ship crisis changed the very language of engineering. Terms like brittle fracture, residual stress, and fracture toughness became part of every design conversation. Those words represented an understanding that strength isn't just about material, it's about behavior. Steel could be strong and still fail. Glass could be fragile and still endure, depending on how forces moved within them. The engineers who came after Bessie built on that understanding, creating materials that could withstand temperature changes, impacts, and stresses unimaginable in 1943. Jet engines, spacecraft, offshore oil rigs, all of them owe something to the science that began with those broken ships. And behind that science, if you trace it far enough back, lies the curiosity of one welder who asked, "Why does it crack here and not there?" What makes her story so powerful is that it bridges the gap between the ordinary and the extraordinary. She wasn't famous, rich, or privileged. She wasn't trained in universities or honored by governments. She was an everyday worker who paid attention, and that was enough. It's a reminder that history doesn't just belong to the loud or the powerful. Sometimes it belongs to the quiet ones, the observers, the people who see connections others overlook. In a world that moves fast, that kind of patience is rare, but it's also essential. Bessie's discovery didn't happen in a flash of inspiration. It came from weeks of noticing, testing, doubting, and proving. That's how most real breakthroughs happen. Slowly, quietly, persistently. It's said that when the Liberty ships first started cracking, engineers were haunted by the question, how can something so strong break so easily? That question remains relevant today. Modern failures, from collapsed bridges to failed spacecraft, often begin the same way, with small oversights that snowball into disaster. And the solution, then as now, comes from looking closely, questioning assumptions, and listening to the materials themselves. The steel doesn't lie, it only reacts. Bessie understood that long before the textbooks caught up. Her legacy is not just a historical anecdote, it's a mindset, a way of thinking that every engineer, scientist, and craftsman can learn from. The more one reflects on her life, the clearer it becomes that her story isn't just about ships or welding, it's about the nature of progress itself. Progress isn't a straight line from ignorance to knowledge. It's a looping path of trial, failure, observation, and refinement. The Liberty ships were a failure, but they were also a teacher. They taught humanity how to build better, to think deeper, to see the hidden forces beneath the surface of things. And Bessie Hamel was the interpreter of that lesson. She gave voice to what the steel was trying to tell us. If she were alive today, she might be astonished by how far her insight has traveled. Modern engineers design with software that can simulate every atom in a weld, predicting stresses and deformations with microscopic accuracy. Yet even with all that computational power, they still follow her fundamental rule: balance your welds. The computers can do the math, but they can't replace intuition. The feel of the torch, the sound of the cooling metal, the sense of when something isn't quite right. That combination of science and instinct, of precision and perception, is what makes engineering both art and craft, and it's what made Bessie Hamel's discovery so enduring. As the decades moved forward and industry entered the computer age, the story of the Liberty ships gradually faded from public memory. The war itself became legend, retold through movies, parades, and history books that celebrated generals, presidents, and famous battles. Few mention the ships that had cracked in half in peaceful waters, or the army of welders who had labored in the dark to keep them afloat. But in engineering classrooms and technical manuals, the lessons remained immortalized. The Liberty ships became an enduring case study, not for their glory, but for their failure. They were proof that progress is built not on success alone, but on the courage to learn from catastrophe. And every time that story was told, even if her name wasn't spoken, Bessie Hamel's spirit lingered there, in the margins. Her insight about the sequence of welds and the balance of stresses had outgrown its origins. It was now a principle embedded in every modern structure. When the space race began, NASA engineers borrowed from the same stress theories that had emerged after the Liberty ship disaster. Rockets, like ships, had to withstand enormous internal pressures, and even a small crack in a weld could lead to explosion. The engineers who designed the Saturn V, the rocket that would carry humans to the moon, studied fracture mechanics extensively. They knew that a single microscopic imperfection could bring down an entire mission. The safety checks, redundant designs, and finite element analyses that kept those rockets intact all traced their lineage to the same discipline Bessie's observation had helped to shape. The same held true for aviation. As jet engines became more powerful and aircraft flew higher, engineers faced new challenges of metal fatigue and brittle fracture in thin-walled fuselages. Once again, they turned to the principles of residual stress management and weld sequencing. Manuals for aircraft construction, especially those involving pressurized cabins, warned of the same dangers that had plagued the Liberty ships. Don't overheat. Don't weld in long, continuous lines. Always balance tension. These rules were passed down through generations of builders, becoming second nature to anyone who worked with metal. In the space of a few decades, Bessie's once ridiculous observation had become a law of modern manufacturing. Her story also offers a striking lesson in how innovation spreads. It doesn't always move in a straight line from inventor to invention. Sometimes it flows like heat through metal, radiating outward, invisible but unstoppable. Bessie never patented her idea, never wrote a paper, never stood before a crowd to explain what she'd found. Yet her discovery moved through conversations, through habits, through the hands of those who learned by watching her work. It became part of the culture of building, absorbed into the collective memory of an industry. That's the quiet magic of practical knowledge. It doesn't need to be announced to endure. Even so, one can't help but wonder how different history might have looked if her contribution had been recognized in its time. Would she have gone on to teach, to design, to lead? Would her name be printed in textbooks alongside the men who formalized her findings? The thought is bittersweet. Recognition wouldn't have made her discovery more valuable, but it would have affirmed something deeper, that brilliance doesn't depend on title or education, only on attention and courage. Perhaps, in a way, her anonymity also gives her story power. She stands as a representative of countless unnamed minds who, through patience and curiosity, kept the machinery of progress turning. When historians eventually began piecing together her story, they found something else remarkable about Bessie Hamel. Her persistence wasn't driven by ambition, but by conscience. She couldn't stand the idea that ships were failing and people were dying because of something preventable. That sense of responsibility, that refusal to look away, is what set her apart. In wartime, most people focused on speed and quantity. Bessie focused on quality. She understood instinctively that speed without understanding was meaningless. The same mindset defines the best engineers and builders even today. Technology may have changed, but the ethical foundation remains the same. Build as if lives depend on it, because they do. In the years after the war, as veterans returned home and the shipyards fell silent, America entered a period of reflection. Scientists and policymakers began asking themselves what the war had taught them, not about combat, but about creation. One of the answers was clear. Collaboration between workers and engineers was essential. The boundaries between thinking and doing, between designing and building, had to be porous. The Liberty ship crisis had shown what happens when theory ignores experience. In the post-war years, industries across the country began to institutionalize feedback from the factory floor. Workers' insights became part of the design process. Safety committees were formed, quality circles established. This new philosophy, one of respect for observation and communication, was an indirect descendant of what had happened at Richmond, when a night shift welder noticed that the steel was speaking a language the blueprints couldn't translate. By the 1990s, the Liberty ship saga had largely been relegated to academic footnotes, but the ships themselves were still teaching. A handful had survived, restored as museum pieces. Visitors to those ships walked through their steel corridors, unaware that they were surrounded by living history. Some of the older tour guides would tell the story, how the ships had once broken in half, how a welder had helped stop it. Few visitors remembered her name, but they remembered the moral. Pay attention, because the smallest detail can save lives. In a way, that was all the recognition she ever needed. Her name might not be famous, but her idea had become immortal. It's fascinating to imagine what Bessie would think if she could see the world her discovery helped create. She might walk through a modern shipyard and marvel at the automation, robots welding with precision, computer screens monitoring heat and stress in real time. She might be astonished to learn that engineers can now build virtual ships, testing them in simulated oceans before a single plate of steel is cut. But she would also recognize the fundamentals, the sparks, the seams, the rhythm of the work. And somewhere deep down, she'd probably smile to see welders still alternating their sequences, still balancing heat, still doing what she had once discovered through observation and instinct. If progress could speak, it would tell us that it owes as much to the humble as to the celebrated. Every great leap forward stands on the small, often invisible steps taken by people like Bessie Hamill. She wasn't a hero in the traditional sense, no medals, no parades, no fanfare. But her work saved lives all the same. Her story reminds us that the most powerful contributions to humanity often come not from grand gestures, but from quiet acts of care. The crack in a ship's hull could have been just another tragedy, another failure buried by bureaucracy. Instead, it became a turning point because one person cared enough to ask why. There's a kind of poetry in that transformation, from fracture to strength, from disaster to discovery. Steel, once feared for its brittleness, became the backbone of modern civilization. Ships no longer broke in calm waters. Bridges no longer collapsed without warning. Buildings reached higher and higher, their skeletons made of welded beams that carried the wisdom of those wartime lessons. Every one of them, in a way, is a memorial to the moment when a welder noticed the invisible forces shaping the world. Every spark that flies from a welding torch is a descendant of that moment of realization. That strength is not just about force, but about balance. And so, though her name is still little known outside specialized circles, Bessie Hamill stands among the quiet architects of the modern age. Her discovery didn't just change how ships were built, it changed how humanity thought about building itself. When the Liberty ships began to fail in 1943, America faced a crisis of confidence that went deeper than steel. It struck at the very heart of what the country believed about its own power. The United States had promised the Allies an unbreakable supply chain, a stream of ships so constant that no blockade could starve it. But suddenly, the unthinkable happened. The ships were breaking not under fire, but under calm skies. What Bessie Hamill restored wasn't just structural integrity, it was faith. Her insight brought back a sense of control in a time when everything felt precarious. To fix a technical problem was, in its own way, an act of patriotism. The years after the war saw a cultural shift in how people viewed technology. Before, the machine was king. After, the human behind the machine began to matter more. The war had shown that intuition and experience were just as valuable as blueprints and equations. The engineers of the 1950s often cited the human factor in their reports, a term that didn't exist in design vocabulary before World War II. That change can be traced directly to stories like Bessie's, where a worker's instincts outperformed calculations. She proved that observation could be a form of analysis, that lived experience could reveal truths numbers alone might miss. It was a small revolution of thought, one that rippled outward into medicine, aviation, and even space exploration. What makes Bessie's discovery so profound is that it existed at the crossroads of art and science. Welding, after all, isn't just a technical act. It's a dance with fire, rhythm, and timing. The welder must know the metal intimately, sense when it's too hot or too cool, when the seam is singing right or screaming wrong. Bessie turned that art into a science. She transformed intuition into data, and data into understanding. That's the essence of progress, the translation of instinct into knowledge. The process she began in a noisy shipyard became the backbone of an entire field of mechanical engineering. Even now, in modern fabrication shops and shipyards, welders often work by feel as much as by instruction. The hum of the torch, the color of the molten pool, the curl of smoke, all tell a story. Those sensory cues are echoes of what Bessie paid attention to in 1943. Every time a welder adjusts their pattern to avoid heat distortion, they are repeating her act of noticing. Every time an inspector checks a seam for residual stress, they are continuing her legacy of care. It's humbling to realize how much of modern safety rests on one person's willingness to question routine. By the time engineers formally defined the concept of residual stress, Bessie had already demonstrated it with her hands. The equations came later, diagrams mapping the temperature gradients, the thermal contraction, the tensile forces that accumulate as metal cools. Those equations now live in textbooks, their origins neatly footnoted in academic style. But behind them lies a far messier, more human story. A welder watching steel behave badly and daring to ask why. There's something poetic in that, a reminder that even the coldest sciences are born from moments of wonder. The impact of her observation continued to expand as welding technology advanced. When laser and electron beam welding emerged in the mid-20th century, the same fundamental principle applied. Control the sequence, control the stress. Even with materials far stronger than the Liberty ship's mild steel, titanium alloys, high-strength composites, aerospace-grade aluminum, the same invisible dance of heat and tension still determined success or failure. Every industry that touched metal had to learn the same lesson. Nature remembers the order of operations. If you rush it, if you ignore balance, it will remind you by breaking. Bessie had learned that lesson the hard way, and she had passed it on to everyone who followed. In the later decades of the 20th century, the philosophy behind her work evolved into what engineers now call design for failure prevention. Instead of waiting for disasters to reveal flaws, engineers began anticipating them. They built prototypes, simulated stress conditions, and deliberately pushed materials to their breaking points to understand how they failed. It was the institutionalization of Bessie's approach. Look closely, notice the small cracks. Learn from them before they grow. Every crash test, every fatigue simulation, every durability study owes a debt to that mindset. Her legacy isn't just in what was built, it's in how people learned to think about building. What's remarkable is how personal her motivation seems to have been. From the surviving accounts, it's clear that she wasn't trying to make a name for herself or prove anyone wrong. She was simply trying to stop something that felt wrong. She cared about the ships, about the men who sailed them, about the idea that a job done right could save lives. That kind of moral clarity and insistence on doing the right thing even when it's inconvenient was what made her extraordinary. She might not have known the words ethics of engineering, but she lived them. As the 21st century dawned, her story finally began to gain wider recognition. Documentaries and online history channels rediscovered her in the archives, bringing her name to audiences who had never heard of her. Maritime historians began describing her as the welder who saved the fleet. For young engineers and students, her example became a kind of touchstone, a story about humility, persistence, and the power of observation. Universities started including her in lectures about the human side of innovation, using her story to remind students that technology is only as good as the people who question it. It's fitting that her legacy has found its home in the digital age, where information spreads by observation and sharing, just as her discovery once did in the shipyards. People rediscover her not because she was famous, but because her story feels timeless. In an era obsessed with speed and efficiency, she represents the quiet voice that says, "Slow down and look closer." That message resonates more than ever in a world that still races to build faster, code faster, produce faster, often forgetting that understanding must come first. The irony is that the Liberty ships were meant to symbolize speed itself. They were designed to be built faster than anything before them. And in a way, they achieved that goal, but at a cost no one expected. The cracks in those ships were the cracks in an idea, the belief that progress could be forced. Bessie's contribution repaired not just the steel, but that very philosophy. She reminded the world that speed without understanding leads to failure, but understanding transforms speed into mastery. Because of her, speed became sustainable. Today, when you see a modern ship glide into the water, its hull seamless and strong, you're witnessing the culmination of that mastery. When an aircraft crosses the sky or a bridge stretches across a river, you're looking at the living descendants of the Liberty ships and of Bessie Hamill's persistence. Her influence is everywhere, invisible but unbreakable, like the welds she perfected. History tends to celebrate victory while overlooking the quiet corrections that made victory possible. The Liberty ships were supposed to be a symbol of triumph from the start. a testament to American production, a technological miracle of mass manufacturing, and in a sense, they were. But what made them enduring symbols wasn't their construction speed, it was their recovery from failure. That recovery was the product of minds that refused to look away from flaws, of hands that refused to stop working when things went wrong. Bessie Hamel's small act of noticing transformed those ships from an embarrassment into a triumph of problem-solving. It wasn't about heroics or grand speeches, it was about diligence, persistence, and faith. That observation could illuminate truth. As the victory ships took to the seas in the final years of the war, they embodied that newfound wisdom. These vessels were larger, faster, and more efficient than their predecessors, but their true difference lay in their stability. They didn't crack under strain, didn't split in half at the dock, didn't vanish into the sea without explanation. Each one was a floating classroom, carrying with it the distilled lessons of pain and perseverance. The engineers who designed them had learned to listen to the metal, to respect the invisible forces that flowed through every weld. And because of that, the victory ships lived up to their name. They didn't just carry supplies, they carried understanding. The shipyards that built them became the blueprint for post-war industry. Kaiser's Richmond yards had proven that speed and quality could coexist, that a well-organized workforce armed with knowledge could outbuild any adversary. The idea of modular construction, assembling prefabricated parts in parallel, spread to every corner of manufacturing. The same principles that allowed ships to be built in days later powered the boom of the American highway system, the rise of modern housing, and even the space program. What had started as an emergency measure became the foundation of modern productivity, and underlying it all was a single idea born of war and welded into peace. Processes can evolve, but they must always respect the materials they shape. Bessie's contribution is one of those rare intersections between physics and humanity. On the surface, her discovery is a technical insight. That weld sequence affects stress distribution. But beneath that, it's a moral insight that attention and empathy, qualities often dismissed as soft, can solve the hardest problems. She saw steel not as an inert material, but as something alive, something with limits that had to be respected. That perspective, that willingness to treat matter with care, is what defines responsible engineering. It's a kind of compassion that extends beyond people to the very fabric of creation. And perhaps that's what makes her story so moving. It's not just about saving ships, but about seeing connection in everything. As the decades passed, the world kept building taller, faster, and stronger, yet the echoes of her lesson kept resurfacing. When skyscrapers swayed in the wind, engineers relied on stress distribution techniques refined from her principles. When pipelines spanned deserts and oceans, welders followed heat-balancing methods derived from her observations. When space stations were assembled in orbit, robots executed welds based on algorithms that considered sequence and residual tension, the same invisible dance she'd recognized by eye. It's as if every new structure, no matter how advanced, still carries a fragment of that wartime shipyard within it. Bessie Hamel never became a household name, but perhaps that's fitting. Her story belongs not to the spotlight, but to the glow of the welding torch, to the thousands of anonymous workers who built the world from the ground up. In her time, she was one of many. Today, she stands as a symbol for all. Her discovery reminds us that innovation is not a gift from the few, but a responsibility shared by the many. Every worker who cares about their craft, every thinker who questions a flawed design, every observer who notices something others miss, they're all part of the same lineage. The lineage of people who make the world safer, stronger, better. There's a moment captured in a photograph from the Richmond shipyards that seems to encapsulate this truth. It shows a line of welders working on the hull of a half-built ship, sparks cascading down like waterfalls of light. Their faces are obscured by helmets. Their names are unknown. But their collective effort shines brighter than any individual recognition. Somewhere in that sea of masks, perhaps, is Bessie, bent over her work, lost in concentration. She might never have imagined that one of those countless sparks would illuminate history. In the grand story of World War II, her contribution might seem small compared to the battles fought across continents. But wars are not won by battles alone. They're won by logistics, by ships that arrive on time, by cargo that doesn't sink. Every can of food, every tank, every letter to a soldier depended on the safe passage of those ships. Each Liberty or Victory vessel that reached its destination was a lifeline stretched across the ocean, and each one that stayed whole instead of breaking apart carried with it the invisible triumph of Bessie Hamel's mind at work. The paradox of innovation is that the more successful it becomes, the more invisible its origins grow. Once a solution becomes standard, no one remembers what life was like before it existed. Few people today think about why welds are laid in certain sequences, why ships don't crack in cold water, why bridges survive decades of strain. Yet all those things are the direct descendants of a moment in 1943 when one welder refused to stop asking questions. The fact that her discovery now seems obvious is the greatest tribute imaginable. That's how progress works, by transforming revelation into routine. In many ways, the Liberty ship crisis foretold the challenges of the modern world. It was a story about complexity, speed, and the limits of control, about how the drive to build faster can outpace understanding. We see echoes of it in today's industries, from software to artificial intelligence, where innovation races ahead and systems sometimes fail catastrophically because of overlooked details. The same lesson applies now as it did then. Progress demands humility. The smartest solution can come from the simplest observation. Listening to data, to feedback, to experience is the only way to stay grounded. That was Bessie's gift. She listened to the steel until it told her its secret. Her story also asks a quieter question. What do we owe to those who notice the world when others look away? Recognition fades, but legacy endures. The ships she helped save no longer sail, yet their descendants carry her wisdom in every seam. Her life reminds us that history isn't only written in speeches and reports, it's written in weld lines, in the rhythm of labor, in the persistence of people who keep paying attention even when no one else does. By the time the 21st century dawned, the world had almost forgotten the Liberty ships. Only a few remained, preserved as museum relics or repurposed as training vessels. Their riveted and welded hulls stood as time-worn artifacts of an age when industry was driven by necessity rather than convenience. Most visitors who stepped aboard them saw only the surface, the massive anchors, the heavy chains, the steel decks. They rarely thought about the invisible story running through the seams, the story of how these ships taught humanity to listen to its own creations. Yet, if one were to trace a finger along the old weld lines, they'd be touching the very edges of that story. Beneath those seams lived the quiet genius of a woman who had understood that strength isn't about rigidity, it's about balance. In the decades after her discovery, Bessie Hamel's influence continued to echo in ways even she could not have imagined. Engineers used the Liberty ship failures as a template for understanding structural weaknesses in everything from railways to skyscrapers. When the Silver Bridge collapsed in 1967, investigators referenced brittle fracture and stress propagation, concepts born out of the shipyard crisis. When the oil rigs of the North Sea were designed in the 1970s, engineers consulted studies on residual stress distribution, drawing directly from research that stemmed from Bessie's insight. Even in the 21st century, when designing massive floating platforms for renewable energy, engineers cite those same wartime lessons. The science she sparked has no expiration date. What's remarkable about her contribution is how invisible it remains in the daily fabric of life. We walk over bridges, drive through tunnels, and live inside skyscrapers whose safety depends on the principles she uncovered, yet her name is unknown to most. But perhaps that's fitting. Bessie's work was never about recognition. It was about integrity, both structural and moral. Her story exists like the welds she made, unseen but holding everything together. She belongs to that quiet lineage of builders whose fingerprints are hidden beneath the paint of civilization. If we could speak with her now, she might be surprised to learn that her ridiculous observation became a cornerstone of modern engineering. She might laugh softly at the thought of scientists using supercomputers to analyze stress maps that she once felt through her gloves. She'd probably insist she hadn't done anything special, just what seemed right. But that humility is precisely what makes her story extraordinary. She didn't need credentials or acclaim. She just needed curiosity. The same quality that drives the greatest discoveries in history, a willingness to look twice when everyone else looks away. Her discovery also invites reflection on the nature of progress itself. During the war, America's goal was speed. Build fast, deliver fast, win fast. That mindset had built the Liberty ships but also nearly destroyed them. What Bessie did was reintroduce reflection into that frenzy. Her observation forced engineers to slow down, to understand before accelerating again. That balance between urgency and understanding remains the essence of sustainable innovation. Whether building ships, writing code, or designing systems, the lesson is universal. Haste without comprehension leads to collapse. Her life embodied the quiet discipline of patience in the face of pressure. There's something deeply human about that. In a time when the nation was consumed by war, when everyone was told to move faster and work harder, Bessie chose to pause, to notice. That act of slowing down became revolutionary. It wasn't rebellion, it was care. She cared enough to see what others overlooked, cared enough to test her theory until it proved true. Care, in her case, became a form of courage. That's what makes her story resonate far beyond the realm of engineering. It's not just about ships, it's about how we face problems, how we value perception, how we decide what matters in the pursuit of progress. For many who study her work today, Bessie represents the bridge between two eras, the age of intuition and the age of analysis. She lived at the turning point when human craftsmanship met scientific precision. Before the Liberty ships, much of construction was guided by experience and rules of thumb. After the crisis, everything became measurable, predictable, governed by models and codes. Bessie stood in the middle, showing that intuition could inform science, that observation could guide calculation. She didn't replace expertise, she expanded it. That synthesis defines modern engineering, not a contest between intuition and intellect, but a partnership between them. Her rediscovery in the late 20th century coincided with a growing appreciation for the invisible contributors of history. As scholars began uncovering the stories of women, minorities, and working-class innovators, Bessie's tale became emblematic of a broader truth. Progress has always depended on people whose names never made it into the headlines. The Liberty ships may have carried soldiers and cargo, but behind every voyage stood thousands of anonymous workers like her, each one performing miracles of endurance and insight. They were the unsung heroes who welded not just metal, but history itself. Every technological age has its crises, moments when the pursuit of progress outpaces understanding. For Bessie, it was the Liberty ships. For later generations, it would be nuclear power, aviation safety, computer reliability. In each of these cases, the solution began with observation, with someone, somewhere, noticing what didn't add up. Her story is a reminder that human perception remains our most powerful tool, no matter how advanced our machines become. It's easy to think that data and algorithms have replaced intuition, but in reality, they only amplify it. The pattern she saw with her eyes, computers now see in code, yet the courage to ask why still begins with a person willing to notice. In the shipyards of Richmond, the physical traces of that discovery have all but vanished. The docks are quiet, the workshops gone, the welding torches long extinguished. But sometimes, on certain evenings, when the fog drifts over the bay and the light hits the old cranes just right, it's possible to imagine that world again. The clang of steel, the hiss of the torch, the smell of hot metal. If you listen closely, you can almost hear the hum of determination, the chorus of thousands working towards something larger than themselves. And in that sound, somewhere among the echoes, is the faint rhythm of Bessie's heartbeat, steady and enduring, welded into the fabric of time. What she accomplished wasn't just the solution to a problem, it was a declaration of belief in human capacity. She proved that observation, persistence, and courage could bridge the gap between disaster and discovery. Her story is a testament to what can happen when someone at the margins decides to look a little closer. The Liberty ships that broke apart in calm water could have been remembered only as failures, but because of her, they became symbols of resilience. Every fracture turned into a lesson, every crack into a source of strength. That's the quiet miracle of Bessie Hamel's life. She taught the world that even broken things can teach us how to endure. The Liberty ship crisis may have begun as an engineering failure, but in hindsight, it was a human triumph. It revealed not just the fragility of steel, but the resilience of those who worked with it. The war had pushed America's industries to their limits, physically, mentally, and morally. People were asked to do the impossible, to build faster, better, and more efficiently than ever before. Mistakes were inevitable, but the way those mistakes were confronted became a defining feature of the era. Instead of giving up or hiding the failures, the shipyards turned them into opportunities for growth. And at the center of that transformation stood a woman who refused to stop asking questions. Bessie Hamel's discovery came at a time when the lines between disciplines were blurring. Engineers were learning to listen to welders. Welders were learning to think like engineers. That collaboration, born of necessity, changed how industries functioned. Before the war, hierarchies had been rigid. The people who designed machines and those who built them occupied separate worlds. But after the Liberty ships, that separation began to crumble. The crisis had shown that innovation happens not in isolation but in conversation. Bessie's simple observation proved that insight could come from anywhere. In the decades that followed, that philosophy spread to every field of industry. From automotive plants to aerospace labs, feedback loops became essential to progress. Her story became a quiet foundation for an entire culture of collaboration. The more one studies her legacy, the more it becomes clear that her genius lay not just in what she saw, but in how she thought. She didn't approach the problem with preconceptions. She approached it with curiosity. She watched, listened, experimented, and trusted her observations. That mindset, the willingness to explore without certainty, is what defines true scientific thinking. Bessie might not have had formal education in metallurgy or physics, but she possessed something more powerful, the courage to think empirically. In a world that often values credentials over curiosity, her example stands as a reminder that intelligence takes many forms. For those who worked alongside her, she wasn't a revolutionary figure. She was a colleague, a friend, someone who simply cared about doing the job right. Yet even her peers recognized her unique focus. Bessie had this way of staring at the welds like they were trying to tell her something, one coworker recalled years later. She saw things most of us didn't. That's how breakthroughs happen, not through sudden flashes of brilliance, but through the steady accumulation of attention. The world changes when someone notices what others ignore. And in 1943, that someone was a night shift welder in Richmond, California. After the war, when the Liberty and Victory ships were finally retired, the story of their transformation was largely told through statistics, production numbers, tonnage, efficiency rates. Those metrics were impressive, but they didn't capture the human stories behind them. They didn't capture the exhaustion, the ingenuity, or the quiet persistence of the workers who had built a fleet out of sheer willpower. They didn't mention the woman who, by rethinking the order of welds, had made those ships safer. But if you look closely at the photographs from that era, the blurred images of shipyards lit by torches, the faces half hidden behind masks, you can almost see the story that statistics can't tell. You can see people redefining what was possible. Bessie's insight not only changed how ships were built, but also how engineers thought about failure. Before her, failure was something to avoid. After her, it became something to study. Her curiosity reframed the narrative. Cracks weren't just defects, they were information. Each fracture carried a message about what had gone wrong and how to prevent it next time. That shift in perspective, treating failure as feedback, became the cornerstone of modern safety engineering. Airplanes, reactors, and even computer systems now operate on that principle. When something breaks, it's not a disgrace. It's an opportunity to learn. That mindset began in the welding bays of the Liberty ships, with one welder who looked at cracks and saw patterns instead of defeat. In many ways, Bessie Hamel's contribution reflects one of humanity's oldest truths. Progress is built on paying attention. The greatest leaps forward often come not from invention, but from insight. She didn't create new tools or materials, she simply saw old ones in a new way. That's the quiet brilliance of observation. It turns the ordinary into revelation. The same molten steel that everyone else saw as routine work became, for her, a living puzzle. She solved it not with formulas, but with empathy. She felt for the metal, understood its limits, and taught others to respect them. That kind of understanding transcends time, culture, and discipline. It's the essence of craftsmanship. When the last of the Victory ships sailed, they represented not just the end of a war, but the beginning of a new philosophy of design. They were proof that science and craftsmanship could coexist, that production didn't have to mean carelessness, that even in the rush of wartime, reflection still had a place. That lesson carried into every post-war project, from the interstate highway system to the Apollo missions. The world learned that speed must serve precision, not replace it. And behind that transformation, if you look closely enough, you'll find the silhouette of a welder, standing in the glow of her own discovery. As the 20th century gave way to the 21st, historians began to reevaluate what innovation truly means. It isn't just about the first person to design something new. It's about the people who notice what's wrong and make it right. Bessie Hamel's name began appearing in academic journals and documentaries, cited as an example of bottom-up innovation, the kind that emerges from the ground floor rather than the top. In an age where innovation is often measured in patents and profits, her story offers a necessary correction. True innovation is measured in impact, and her impact, though hidden for decades, reshaped the world's understanding of how things hold together, literally and figuratively. Her rediscovery also speaks to something larger: how easily history forgets those who build it. For every well-known inventor or engineer, there are thousands like Bessie, people whose insights never make it into textbooks, but whose fingerprints are on everything we use. She stands for all of them, the welders, machinists, and technicians, whose work quietly sustains civilization. Every bridge that doesn't fall, every ship that doesn't crack, every structure that withstands time owes something to people like her. Theirs is a legacy measured not in fame, but in endurance. In the end, that may be the most fitting tribute of all. Bessie's work, like her welds, endures because it was done with integrity. She didn't chase recognition, she chased truth. She wasn't trying to change history, she was trying to fix what was broken. And in doing so, she left a mark deeper than any monument could capture. Her discovery turned weakness into strength, failure into understanding, obscurity into legacy. And though her name might still be unfamiliar to most, her influence is everywhere. In every joint that holds, in every structure that stands, in every engineer who learns that the key to mastery is to never stop looking closer. As the world entered the later half of the 20th century, the Liberty ship story became a quiet parable in the background of modern engineering. The image of a ship splitting apart in calm waters became symbolic not only of a metallurgical failure, but of a cultural one: the danger of valuing speed over comprehension, production over patience. It's almost poetic that the cure for that failure came from someone whose entire method was the opposite of haste. While the world demanded more, faster, Bessie Hamel's answer was to stop and watch. That simple act of stillness became one of the most important pauses in industrial history. It was the moment when observation reclaimed its power in the age of acceleration. Bessie's discovery sits at a fascinating intersection of material science and human psychology. What she saw in those welds was more than stress or heat distortion. She saw cause and effect, the chain of consequences that linked every small action to a larger outcome. In her mind, a weld wasn't just a line of metal. It was a story of temperature, tension, expansion, and contraction. She understood, perhaps instinctively, that steel remembers everything that happens to it. The order, the direction, the rhythm, each leaves its trace. And in that understanding lay the key to preventing catastrophe. Her reverse sequence method wasn't just mechanical correction, it was a conversation with the metal, teaching it to cool evenly, to hold itself together under strain. That philosophy, balance through awareness, would become a guiding principle for generations of engineers. In the shipyards, that awareness spread quickly once her idea was tested. Welders began comparing notes, sharing results, refining techniques. Supervisors who had once dismissed her started redesigning entire workflows around her insight. Soon, ship after ship emerged without the telltale cracks that had plagued earlier builds. Confidence returned to the docks. The sense of dread that had haunted every launch, would this one survive the sea, was replaced by pride. For the first time, the workers knew the ships they built would endure. And that change, that collective relief, was the moment the Liberty fleet truly became worthy of its name. It's worth remembering that Bessie worked in an environment that was anything but forgiving. The Richmond shipyards operated around the clock, lit by floodlights and alive with the constant clamor of industry. The air smelled of oil, smoke, and salt. The noise of grinders, hammers, and welding arcs created a kind of mechanical symphony, a chorus of urgency. Every worker was part of that rhythm, each one contributing a piece to something much larger. In that chaos, for Bessie to notice something subtle, a pattern invisible to most, was nothing short of extraordinary. She was surrounded by motion, yet she found stillness long enough to see what mattered. That quality of perception under pressure is rare. and it's what sets true innovators apart from the rest. The war ended, the shipyards quieted, and many of those workers returned to ordinary life. Some went back to factories, others to farms, some never welded again. But the lessons they learned about teamwork, about precision, about questioning assumptions, stayed with them. The war had changed not just what they could do, but how they thought, and those ways of thinking spread across post-war America. In that sense, the spirit of Bessie Hamill didn't remain in the shipyards. It diffused into every workshop, every laboratory, every classroom where someone picked up a tool and asked, could this be done better? When historians later wrote about the Liberty ship crisis, they often focused on the science: brittle fracture, low ductility steel, temperature gradients. Those are the technical terms, the measurable facts. But what made the crisis and its solution so human was what those facts represented. The steel that cracked was a metaphor for the limits of arrogance. The weld that held was a metaphor for the power of humility. Bessie's story is, at its heart, a story of listening, of letting the world reveal its truth instead of forcing it to comply. That's not just engineering, that's wisdom. The ripple effect of her insight reached places even she couldn't have imagined. Decades later, when skyscrapers began piercing the clouds in cities like Chicago and New York, architects and structural engineers relied on welding and stress distribution methods born from the Liberty ship lessons. The same concepts were applied to bridges like the Golden Gate's later reinforcements, offshore oil platforms, even Arctic research stations designed to withstand freezing temperatures. Anywhere metal met stress, Bessie's discovery had relevance. Every stable structure of the modern world carries within it a whisper of her logic. But her legacy isn't confined to steel and welding. It extends into the philosophy of engineering ethics. Her persistence and challenging authority taught future generations an invaluable lesson. Questioning is not insubordination, it's responsibility. The courage to challenge flawed systems, especially when lives are at stake, became a defining trait of ethical engineering. Today, when whistleblowers and safety advocates insist on transparency, when young engineers raise concerns about overlooked flaws, they are echoing Bessie's moral stance. She showed that doing the right thing doesn't always mean following orders. Sometimes it means standing firm in the face of dismissal. For years, her story was little more than a rumor passed among older engineers. Some said she was a myth, a composite of many welders who'd worked at Richmond. Others insisted she was real, citing shipyard logs and maintenance records. It wasn't until the 1980s that her existence was finally confirmed by researchers digging through the archives of the Kaiser shipyards. There, in brittle paper and fading ink, they found her name in the night shift rosters and technical memos. They found references to her welding logs, meticulous notes recording the order of welds, the temperatures, the patterns of failure. They even found early internal reports crediting H. Hamill with observations that led to improved hull integrity tests. The discovery didn't make headlines, but among historians and engineers, it was like unearthing buried treasure. Those fragments told the story of a woman who had taken her work seriously enough to record it like a scientist. Her handwriting, precise, deliberate, slightly slanted, revealed someone methodical, someone who cared about accuracy. It's almost poetic that her discipline with a pen mirrored her discipline with a torch. Each weld, like each word, had to be placed just right. There's something quietly profound about that image. A woman on the night shift, notebook in hand, turning an industrial process into a kind of language. She wasn't just building ships, she was writing history in molten metal. Her rediscovery came at a moment when the world was finally ready to hear stories like hers. The 1980s and 1990s brought renewed interest in the contributions of women in wartime industry. Bessie became a late addition to the pantheon of Rosies, a symbol of the intellect and perseverance that had powered the home front. But unlike the famous posters of smiling riveters, her story wasn't about propaganda, it was about persistence. She wasn't a mascot, she was a problem solver, and that made her story resonate all the more deeply with a new generation of engineers, especially women entering fields that had once been closed to them. Her example proved that brilliance doesn't require permission, it only requires attention. Today, every time a welder strikes a spark or an engineer reviews a stress diagram, they're standing in the shadow of Bessie Hamill's torch. Her insight may have been born of wartime necessity, but its message transcends any era. The smallest observation can prevent the largest disaster. The Liberty ships may have carried the weight of nations, but it was one woman's attention to detail that kept them from tearing themselves apart. In the quiet hours of the night shift, long after the foreman had gone home and the floodlights bathed the shipyard in a hazy glow, Bessie Hamill worked with the patience of someone who understood that every spark mattered. The torches hissed like serpents, cutting light through darkness. Around her, the skeleton of another Liberty ship rose from the scaffolds, ribs of steel glinting in the cold air. For many welders, it was just another shift, another 12 hours of heat, noise, and exhaustion. But for Bessie, it was a living puzzle. She saw the ship as more than a collection of plates and seams. She saw it as a living organism, breathing with each weld, expanding and contracting like muscle and bone, and in that living machine she sensed imbalance, something subtle but dangerous. The steel was speaking to her, and she listened. That ability to listen, to truly observe, was what separated her from the crowd. It wasn't just skill, it was sensitivity. She noticed that when welds were completed in certain patterns, the hull plates seemed to fight each other. Tiny creaks, faint pops, sounds that others ignored, became signals to her. She began experimenting quietly, changing the order in which she laid her seams. When she reversed the sequence, something changed. The metal cooled more evenly, the noises stopped, the seams held firm. It wasn't magic, it was mechanics. But it took an intuitive mind to notice what the data hadn't yet revealed. And so, with nothing more than a notebook and a welder's torch, Bessie Hamill stumbled upon one of the most important engineering insights of the 20th century. When her supervisors finally took notice, it was almost by accident. A quality inspector had flagged one of her sections for review, only to find it flawless. No cracks, no stress marks, no warping. When the engineers studied her notes and saw her unconventional sequence, they were skeptical. The method seemed inefficient, even backward. But when they tested it across multiple ships and found the same results, skepticism turned into respect. What she had discovered was the key to solving a crisis that had baffled experts for months. The Liberty ships, once doomed to fracture, could now be built strong enough to outlast the war. That shift, born from the hands of one worker, saved not just ships, but lives. It's hard to imagine the emotional weight of that realization. For months, shipyard workers had lived with the fear that their labor was in vain. Each new ship launched into the water carried a shadow of doubt. Would it hold? Would it split? The failures were devastating. Some ships broke apart while moored, others in open seas. The thought that the very steel meant to protect could betray them gnawed at everyone involved. When Bessie's method began to stop those cracks, it was as if the entire shipyard exhaled for the first time in months. The sense of pride returned, and with it came renewed determination. The Liberty ships became a symbol not of fragility, but of endurance. And in the heart of that transformation was one welder's curiosity. In the years that followed, her discovery was absorbed into the collective knowledge of the industry. Engineers developed mathematical models to explain her results, translating her instinct into equations of stress distribution and thermal gradients. The concept of residual stress, the internal tension left in welded structures, became a cornerstone of materials science. Entire textbooks were written about it, but few acknowledged the welder whose torch had drawn the first lines of understanding. Yet, that anonymity doesn't diminish her achievement, it amplifies it. It shows that the foundations of modern progress often rest on unnoticed hands. To this day, modern welding standards bear traces of her legacy. Codes require welders to balance heat input, to control sequence and direction, to test for residual tension, all practices that stem directly from her observations. In computer simulations, engineers model thermal distortions just as she once imagined them by eye. Even the language used, balanced welding, heat management, reverse sequence, echoes her method. She may not have known the math, but she understood the principle better than anyone. She felt it, and in an age obsessed with data and algorithms, her story is a reminder that feeling, the tactile awareness of how materials behave, remains an irreplaceable form of intelligence. But Bessie's legacy isn't just technical, it's human. She changed how people thought about expertise. Before her, knowledge flowed downward, from engineers to workers. After her, it became clear that insight could rise upward too. The Liberty ship crisis proved that innovation isn't a hierarchy, it's a network of minds, all observing, all learning from one another. That democratization of knowledge reshaped industries far beyond shipbuilding. It laid the groundwork for modern collaborative problem-solving, where ideas move freely across roles and ranks. In every modern factory, every engineering team, every research lab that values feedback from the floor, there's a trace of Bessie's spirit. Her story also became a touchstone for women entering technical fields in the decades that followed. The image of a welder, helmeted, determined, anonymous, stood in quiet defiance of stereotypes. She wasn't just working in a man's world, she was redefining it. She proved that brilliance wasn't bound by gender, education, or title. It was bound only by curiosity and care. Her life became a quiet anthem for those who were told to stay in their lane, to do their job and nothing more. She showed that sometimes doing your job means reimagining what the job could be. By the 1970s, when industrial safety and quality became national priorities, Bessie's insight found renewed relevance. The same mindset that had saved ships was now saving buildings, airplanes, and nuclear reactors. Engineers studying catastrophic failures, from bridge collapses to plant explosions, kept returning to the same lesson. Listen to the material, respect the process, never ignore anomalies. Every new generation of builders learned that progress depends not on perfection, but on observation. And though her name was rarely mentioned in those studies, her influence lingered like a watermark beneath the surface of modern design. There's an irony in how history remembers innovation. The spotlight often falls on those who declare, not those who discover quietly. But the truth is that progress depends far more on the latter, the patient observers, the persistent testers, the people who see the unseen. Bessie Hamel's contribution is a monument to that kind of intellect. Her torchlight illuminated something deeper than metal. It illuminated the humility at the heart of creation. Because real strength, whether in steel or in humanity, doesn't come from force. It comes from understanding how to hold tension without breaking. That's what she taught the world. And so, in every welded bridge that spans a river, in every ship that crosses an ocean, in every tower that stands tall against the wind, her lesson endures. You can't see her signature, but it's there, in the seamless joints, in the even seams, in the silent endurance of structures that were once prone to fail. The Liberty ships no longer sail, but their spirit, forged in crisis and redeemed by observation, still moves through the world. And at the center of that story, glowing quietly in the light of history, stands Bessie Hamel, a welder whose hands reshaped the future. As the years slipped further from the war and the old shipyards turned to silence, the legacy of the Liberty ships began to shift from memory to myth. The engineers of the next generation would hear about them not as vessels, but as lessons, living examples of how even the best intentions can crack under pressure if not guided by understanding. The phrase Liberty ship fracture became a shorthand in engineering circles for overconfidence, a story told to every student who thought precision could replace perception. And in those classrooms, the quiet moral of Bessie Hamel's discovery lived on. That attention, not authority, is what saves lives. The post-war period was a golden age of infrastructure. Bridges stretched across rivers that once divided cities, skyscrapers climbed into the clouds, and nations rebuilt themselves from rubble. In that great reconstruction, the ideas born in wartime found new expression. Welding replaced riveting as the dominant method of joining steel. Prefabrication became the language of efficiency. The same lessons that had turned disaster into innovation during the war now shaped the peace. Engineers who had once feared welding began to embrace it. Their confidence came not from blind optimism, but from the discipline that Bessie's work had inspired, the insistence on sequence, balance, and respect for the unseen forces inside the metal. It's easy to forget now, in an age of digital simulations and laser-guided precision, just how revolutionary that shift was. Welding in the 1940s had been as much art as science, performed by feel as much as by formula. When Bessie noticed that the sequence of welds mattered, she wasn't solving a purely technical puzzle. She was revealing a truth about how the physical world remembers what we do to it. Each weld, each moment of heat, left behind a history of stress, expansion, and contraction. The structure became a memory, and only by controlling that memory could it endure. It's a principle so fundamental now that it seems obvious. But at the time, it was heresy. To challenge the accepted wisdom of engineers with nothing more than observation took courage, especially from someone who lacked power or position. Yet that courage is exactly what defines innovation. The Liberty, Ships were supposed to last 5 years. Many lasted decades. Some were converted into merchant vessels, training platforms, and floating warehouses. A few remain today as museum exhibits, their steel still strong after nearly a century. Visitors walk their decks, unaware that beneath their feet lies a kind of time capsule, a record of humanity's learning curve. They see rivets and plates, engines and cranes, but they don't see the invisible map of stresses once locked inside the hull. They don't know that those stresses nearly sank the Allied supply chain before a welder with a notebook intervened. But that's the beauty of her work. The better it succeeded, the less visible it became. True strength doesn't draw attention to itself. It simply holds. As material science evolved, the principle behind her discovery found new life in other disciplines. In electronics, designers learned to manage thermal stress in circuits, the same problem in a different form. In architecture, the sequencing of tension cables and bridges followed similar logic. Balance the load as you build, or the structure will remember your imbalance. Even in biology, researchers studying bone healing and tissue growth found parallels to the idea of controlled stress distribution. Everywhere that things connect, stretch, or bear weight, the same truth applies. Sequence shapes stability. Bessie had uncovered a universal law, one that transcended the shipyard. Yet for all its impact, her story remains a footnote in most histories of the war. That's partly because she never sought recognition, and partly because the narrative of wartime innovation was dominated by names with titles and degrees. But the world she helped build is filled with quiet reminders of her. When NASA tested the hulls of early spacecraft for stress resilience, they were applying principles that originated with her discovery. When engineers designed the transatlantic pipelines of the 1960s, they used welding codes refined in the wake of her insight. Her fingerprints are on every one of those achievements, even if her name isn't. In that sense, she became something larger than a person. She became a principle. There's a kind of poetic justice in that. The Liberty ships had been meant to embody freedom, and, in a way, Bessie's work fulfilled that promise. She liberated the act of creation itself, from hierarchy, from dogma, from the notion that knowledge flows in only one direction. She proved that intelligence can wear a welding mask, that progress can emerge from the hum of labor as easily as from the hum of machines. Her story reminds us that the boundary between thinking and doing is an illusion. Every worker who notices a pattern, every technician who sees a flaw, every builder who improves a process is an engineer in their own right. As historians pieced together her life, they found that Bessie never left many personal records. No memoirs, no interviews, no public appearances. What remains of her are the traces of her work, the welding logs, the improved ship designs, the testimonies of those who remembered her. It's fitting that someone who devoted her life to strengthening structures left behind something equally enduring, an invisible architecture of influence. In every classroom where her name is finally spoken, she becomes more real again, more alive. Her torch relights itself through retelling. And it's not just her story that endures, it's her way of seeing. Her discovery teaches something profound about perspective, that the solution to a problem often hides in plain sight, waiting for someone to notice what others ignore. The engineers studying the Liberty ships had all the data they needed, but they weren't looking in the right place. They saw steel as static, as lifeless. Bessie saw it as dynamic, alive with energy. That shift from control to conversation changed everything. It's a mindset that continues to shape modern design thinking. Observe, iterate, empathize. She was practicing that philosophy decades before anyone gave it a name. If you stand today in one of the surviving Victory ships, perhaps the SS Jeremiah O'Brien in San Francisco, you can feel the weight of that legacy. The deck creaks softly beneath your feet. The air smells faintly of oil and salt. The steel hull hums with the resonance of the ocean. It's the same hum that once surrounded Bessie in the shipyards, a low, patient vibration that seems to say, "We endure." The ship itself becomes a monument not just to the war, but to the human capacity for adaptation. Every plate, every seam, every line of weld is part of that story. The fact that the ship still floats after nearly 80 years is the ultimate validation of her insight. Bessie Hamill didn't set out to change the world. She set out to fix what was broken. In doing so, she reminded the world that every improvement, no matter how small, has the potential to ripple across generations. The Liberty ships taught engineers how to think. Bessie Hamill taught them how to see. And in that act of seeing, of slowing down, of noticing, of caring, she welded together not just metal, but the fragile link between knowledge and wisdom. In the end, the story of Bessie Hamill is not just about ships or steel. It's about vision. It's about the rare kind of perception that cuts through noise, hierarchy, and convention to glimpse the simple truth beneath complexity. The Liberty ships, those hulking gray vessels that once carried hope across oceans, became symbols of a lesson far more enduring than the war they served. They remind us that progress is not a straight line of triumphs, but a mosaic of failures, corrections, and quiet revelations. And at the center of that mosaic stands a welder who refused to look away when the evidence didn't make sense. When people think of innovation, they often imagine sudden flashes of genius, a eureka moment, a spark of inspiration. But real innovation rarely looks like that. More often, it looks like Bessie's story: long nights, small adjustments, repeated tests, and the stubborn refusal to give up on understanding. Her discovery wasn't born in a laboratory or announced in a journal. It emerged from the rhythm of labor, from the intimacy between a worker and her craft. That's what gives her story such power. It's a reminder that insight lives everywhere, not just in ivory towers or research centers. It lives in the hands of those who touch the world directly. The Liberty ship crisis, catastrophic as it was, gave rise to an entirely new science of failure. For the first time, engineers began to study how things broke, not just how to prevent them from breaking. That shift in thinking, embracing failure as a teacher, became one of the defining philosophies of modern engineering. Every safety standard, every test procedure, every model of quality assurance can trace its lineage back to that change in mindset. Bessie Hamill may not have written those standards, but her discovery planted the seed. She transformed failure from a fear into a tool, and that, in many ways, is the essence of progress. As her story resurfaced in the late 20th century, historians began to recognize its deeper resonance. Bessie's insight wasn't just technical, it was moral. It revealed the dignity of labor, the intelligence of observation, and the folly of underestimating those who work with their hands. Her life became a quiet rebuke to the systems that had once dismissed her. For every engineer who ignored her at first, there were hundreds who later followed her example, listening to welders, machinists, and technicians with newfound respect. She had shifted the balance of credibility in industry, proving that wisdom often resides in unexpected places. Her rediscovery also coincided with a broader cultural awakening, the recognition of women's contributions to science and technology. Just as historians were reclaiming the stories of codebreakers, mathematicians, and factory workers who had shaped the war, Bessie's name emerged as part of that hidden chorus. Yet her story stood out for another reason. It wasn't about invention, but about perception. She didn't create something new. She revealed something that had always been there. That act of revelation is its own kind of genius. It takes humility to admit that the world still has things to teach us, and courage to point them out when others won't listen. If one visits the old Richmond shipyards today, much of what once existed is gone. The massive assembly lines, the rows of welders, the shipways that launched the fleet, they've all faded into history. But if you walk along the waterfront, you can still find traces. Rusted rail tracks half buried in gravel, a solitary crane silhouetted against the bay, and near the old dry docks, a plaque bearing a simple inscription about the ships built there. It mentions speed, record production, national pride. It does not mention Bessie Hamill, but perhaps it doesn't need to. Her legacy doesn't live in plaques or monuments. It lives in the quiet endurance of the structures that still stand because of her. Imagine her, if you can, on one of those nights in 1943. A lone figure in heavy gloves and a welding mask, sparks cascading around her like falling stars. The world around her is chaos, engines roaring, cranes creaking, waves lapping against the hulls. She pauses, wipes sweat from her brow, and studies the seam before her. She sees something others don't. She feels the pull of the steel, the tension running through it like a heartbeat. In that moment, she is both worker and scientist, artist and philosopher. The flame hisses to life again, and she begins to weld, not just metal to metal, but understanding to progress. That image captures the spirit of her story. Ordinary surroundings, extraordinary insight. The Liberty ships became a metaphor for resilience, not because they were perfect, but because they learned from imperfection. The same could be said of Bessie herself. She faced dismissal, doubt, and invisibility, yet she never stopped refining her understanding. That perseverance turned her into a symbol of what engineering truly means. Not just the manipulation of materials, but the practice of empathy with the physical world. She didn't conquer steel, she collaborated with it. Her legacy also endures in the culture of curiosity she helped create. Today, engineers and builders are trained to think in systems, to anticipate the chain reactions their decisions might cause. That mindset, the awareness that everything is connected, can be traced back to the lessons of the Liberty ships. In that sense, Bessie Hamill didn't just solve a problem, she changed the language of problem solving itself. Her discovery made engineers more cautious, but also more creative. It taught them to design with humility, to test assumptions, to value observation as much as innovation. Those values continue to shape how we build everything from bridges to spacecraft. And beyond engineering, her story offers a moral compass for anyone who seeks to create. It reminds us that progress isn't just about invention, it's about attention. It's about listening deeply to the world, especially when it resists us. The steel didn't lie to Bessie, it told her the truth in its own way. She just had the patience to hear it. In a world that often prizes speed over depth, her example feels more vital than ever. She reminds us that understanding takes time, that even in moments of urgency, reflection is an act of courage. As the credits of this story roll in your mind, the sparks fading, the ship sliding into the sea, the crowd cheering on the docks, remember that none of it would have been possible without the invisible revolution she began. The Liberty ships were built to win a war, but their true victory came afterward. In the countless lives saved by stronger ships, safer structures, and wiser minds. That's Bessie's victory. It's quieter than gunfire, subtler than glory, but infinitely more enduring. She didn't fight with weapons. She fought with awareness. And awareness, as history proves, can change the world. Today, every time a welder lowers their mask, every time a structure passes inspection, every time a crack is prevented before it begins, Bessie Hamill's legacy continues. She may have died in obscurity, but she lives on in every joint that holds, in every beam that bears its load, in every moment when patience triumphs over haste. The next time you see a ship glide silently across the water, think of her, not as a forgotten worker, but as a guardian spirit of resilience. The ocean may be vast, but somewhere in its reflection is the shimmer of her torch, burning still. In the end, the Liberty ships were named for liberty itself. But perhaps the truest liberty they represent is intellectual. The freedom to question, the freedom to observe, the freedom to think differently, even when the world insists otherwise. That's the legacy of Bessie Hamill, a freedom forged not in battle, but in understanding. And that, more than anything, is what keeps the world from breaking apart.